That might sound odd, but you'll see why we're doing that.
Okay, so
we're now going to back up in time a little bit. And we're going to keep the reference level. Notice the picture in the book.
There we go. This is actually going to be part of a chapter that we did a little bit of a while ago. Remember way back when we did projectiles? That was part of chapter 6, which was called Motion in Two Dimensions. At that point, we went to projectiles because it had a lot of similar stuff with the kinematic equations, free fall equations. So we kind of did it all with that stuff. So we're coming back to it now for circular motion. And why we waited for now for circular motion, because we needed to know stuff about Newton's laws and forces for some of the stuff in here, which we just kind of wrapped all that stuff up. But before I get to the simulation, let's make this big for a second so everybody can see. The simulation has like a ladybug moving in a circle, but on a screen, on a 2D screen up right, like you'll be looking at up here, it looks like a vertical circle, right? Like this. What was just up there. But we'll get to study in vertical circles. Probably early next week, maybe late this week. But the easier type of circular motion to study, to start off with, is going to be what we call horizontal plane circles. That would be, so we got to imagine, even though on the screen, when we look at the simulation, although the ladybug's moving in a circle like this, imagine it's moving in a plane like this, okay? So this is what we call a horizontal plane circle, circular motion, because it's in the x-plane, right, as it goes through its circular motion. You could have something kind of in between, too, but mainly we're going to focus on horizontal plane, and later, a couple days in, a vertical plane circle. Now, the reason why we wait for the vertical plane a little bit is because there's something that matters a little bit more in this plane with circular motion as opposed to this plane. What is it? Yeah. Gravity. In this plane, there's no real minimum speed necessary for this thing to continue to go in a circle, is there? As it slows down, it continues to go in a circle if it was in the first place, right? In this plane, since we all know gravity acts on the y-axis only, or hopefully remember that, as it slows down, it won't make a full circle anymore once it gets to be beneath some minimum speed. So that makes it a little bit more complicated mathematically, but not a lot. So that's why we usually take care of that after we go over the more basic horizontal plane circle. All right, so my question, first question is going to be, though, before I get to looking at the simulation, is figuring out what would happen if we released whatever's making the object go in a circle. If you can't see real well, this is just a rubber stopper, like chemistry you use or something like that, okay? And obviously, what is making this stopper go in a circle? Yeah. I am spinning it. So if you're saying me, it's still not 100% right. Because I'm not physically touching it. I'm making it go. I started it. I provided the initial everything to get going. But what is physically making it go in a circle? Yeah. The rope itself. Because that's what's directly attached to it, right? And we all should know by now what we call force when forces on strings, ropes, chains, cables. What's that? Yeah. Tensions, okay? Now, tension isn't the only thing that can make something go in a circle. For this particular example, it is, right? So my question is, what if I release this rope so there's no more tension in it while it's going in a circle? What will happen? Yeah. It will fly off. Be more specific. How? Yeah. In a straight line. Okay? So I'll do it with this, and then we'll see the simulation that you'll slow it down, and we'll have a name for that, of how it flies off in a straight line, a special name. So basically, when I release it, it went straight, right? Now, it did curve down because of what? Yeah, gravity. However, if we had a gravity switch and turned it off, it would have just went straight that way without falling down, right? So that tells us one big thing about circular motion. That if you release something, the force that was making it go in a circle, it can't go in a circle anymore, can it? Right? it didn't even kind of go in a circle anymore. It went in a straight line that way, right? So that's one of the most important things to note. And now I'm going to go to a simulation. So now this isn't the rubber stopper, but imagine it was. This is the only simulation I could find on this. It's a ladybug going around, but imagine this object is attached to a string like it was in this example, just for the time being, okay? And this is a horizontal plane circle, even though it looks vertical on the screen. So what this one traces a little path for us. And let's say, I'll let it come around one more time. When it gets to this bottom position right here, I'm going to go ahead and release whatever's making it go in the circle by clicking this button and pause it. So we can see still the faded circular path that it was still going in, right? And this straight line is exactly what will happen. Lakin was right. It went in a complete straight line. There's a geometry term that we attach to it to explain this better. How many are you familiar with, I don't know when you guys all took geometry, probably not that long ago, the term tangent to a circle? Now be careful, we're probably familiar with tangent applied to SOHCAHTOA and trig functions, right? This has a different meaning in geometry when we say tangent to a circle. Have any of you ever heard that before? Or recalled that? All right, maybe you did, maybe you didn't, but here's what a tangent line to a circle is, as defined in geometry. It's a line that touches a circle in only one spot on its circumference, and it's perpendicular to the radius. So I can't draw a radius in here, but we all know what a radius is, right? It's a line that went from the center of the circle out to the edge, right? So if I drew a radius to the release point, that looks pretty perpendicular to the release line, right? So that's why we say it flies off tangent to the path. So anything at any moment, anything that's going in a circle, for any reason, if you cut off the force or forces in some cases that make it go in a circle, it will, if you cut them off 100%, like me letting go of that line, it'll fly off in a straight line, tangent to the path of travel. Let me make it go in a circle again. So if I did it at some other spot in the circular path, if I hit the release button right now, it does the same thing at that point. It releases tangent as soon as I let go of whatever force was making it go. And so that's one of a handful of some of the most important stuff that we study with this. Now back to it just traveling in a circle. Let's ask you guys some, describe this. The other ones will fade away here in a second. All right, other than the fact that this object is going in a circle, what could you say maybe about its velocity? What does it look like? Other than the fact it's going in a circle. You were describing something to me, how this object is moving, how it's traveling. What's another thing you might be able to say about this particular object? Yeah. Good, and you said it right, because most people don't. It has a constant speed. What if somebody raised their hand right then and said it has a constant velocity? What problem is that? Yeah, Josh? Exactly. We still got to remember something we learned like first week of school, right? That velocity is a vector, means it cares about what? Yeah, direction. So we can't ever say anything that's going in a circle, or not even a full circle. This could be a partial turn, like a car going around a turn. It doesn't even have to be a perfect circle for all this stuff to apply. If anything's going through a turn, it is incorrect to say it's going with constant velocity, because velocity cares about magnitude and direction. When you're going through a circle or a curve, every moment you're changing direction, right? Every single moment. So it's going in a constant speed would be the really only other thing we could describe about this thing other than going in a circle. And now I'm going to click on some vectors we could show with this stuff. The velocity vector at any moment points like this. It points the way it wants to fly off, doesn't it? How we showed earlier. That is why it wants to fly off. Every moment it wants to fly off, but whatever's making it go in a circle is not letting it. All right? Later today, or if we don't get to do it today, tomorrow, we're going to go over a handful of forces that commonly make things go in a circle. Now, you just saw me with a object on a string, right? Flinging it around. If this was truly just a ladybug walking in a circle on a flat ground, there's no string attached. What's making the ladybug go in a circle? It's a force you're already familiar with. Go on. It starts from there, but it's not that itself. You're on the right track. The ladybug has to make itself go in the circle, right? Just like if you were walking in a circle, you provide the energy, but the direct force that's actually causing it, the direct force, that's what we're looking for. Sometimes it's easier to think about, well, if this wasn't there, it couldn't go in a circle. All right, let's put it in this way, because we'll have many problems, or a handful of problems at least, on a similar thing. Let's say this isn't a ladybug going around a turn or going around a circle. Let's say this is a car rounding a turn, a flat turn in like the parking lot. What's necessary for that to happen? Yes, friction, exactly. Because yeah, that ladybug, like Bohan, you said, is making herself walk, right? The energy and what we'll eventually call work done from that. But it's the friction between the feet of the bug or the feet of a person when they walk in a circle or the tires in the road that actually is the physical contact force that's causing the circular motion. Because all of a sudden, if you're rounding a turn in a vehicle and it turns into a complete sheet of ice, are you going to round that turn anymore? No. All right? Or if this ladybug or person's walking in a circle, if there's no friction, your feet just start to slide, right? And you just slip off. And if you were going in a circle in the first place and then it like shut off, then you'd go flying off tangent to the path like we said. So velocity always points, that's how we're going to describe it, tangent to the path. So because of that, sometimes, not all the time, but sometimes you'll hear it referred to as tangential velocity. We'll get the formula in a second. And since we said this is moving at constant speed, this makes this type of circular motion a specific type. It is called uniform circular motion. And that's actually specifically the kind we're going to study. Right? When something is going at a constant speed in a circle or partial circle, we say it's uniform circular motion. Uniform basically means the same thing as constant. Okay? Now, could we speed up and slow down while we're going around a turn? Yes. But usually at this level of physics, we're really just focused on the circular factors of it and not worrying about the typical old speed up, slow down stuff. If we go way back to when we first learned about acceleration, that was like prior to you guys ever getting your books, when we were still working off a lot of that website and those study guides. We stressed that there were 3 ways to accelerate. 2 of them, which we studied in detail a lot by this point, but one of them we named way back then, but said it's going to be a while till almost halfway through the year till we get to this one. So what were the 3 ways to accelerate? 2 out of 3, we've already studied a lot with the kinematic equations. Yeah. Good. Speed up, slow down, and change direction. So we've done a lot with speeding up, slowing down stuff, right? All throughout the year, through kinematic equations, through Newton's laws, all that stuff. But we haven't really had any problems where we change direction, like this at least, right? So even though this object is going at a constant speed, it's still accelerating, isn't it? Not for reasons, the first 2 basic reasons. It's not speeding up, it's not slowing down. It could be, but it's not. But it's clearly changing direction. And the definition way back when of acceleration was change in velocity over time. So we already identified velocity was changing due to direction, therefore acceleration has to be. But we kind of call this type of acceleration, the kind due to changing direction, we give it a special name because it is a lot different than speeding up and slowing down. It's still a change in velocity over time, but not in the same nature. It doesn't change the magnitude of it, does it? It's staying at that steady speed, the magnitude. It's changing it because of direction, so we call it centripetal acceleration. How many of you ever heard that term before? You'll see it spelled in a second. It's centripetal. All right. There's another word, though, we'll probably get to discussing tomorrow, that sounds a lot like that. That's actually a kind of a false force. It's often a common misconception. But the word is centripetal. And that fancy word in some other language means towards the center. So the centripetal acceleration is something going through a turn or around a circle. If we drew it as a vector, because we should all know acceleration is a vector, it cares about direction. If I click on it, acceleration always points towards the middle. So somewhere right here would be the center of the circle, right? Notice the acceleration's main vector is maintained right there. Centripetal means towards the center. There's no acceleration in uniform circular motion anywhere else. Now, if we go a little more advanced, which in this course we usually don't, but like in a college physics, you'll take it a little further. You could have this thing speeding up or slowing down, right? As it's also doing this. In that case, you could have a second acceleration vector that is also tangent. So if there is speeding up or slowing down, there'd be another acceleration vector of a different type, just regular speed up, slow down. But it's not present here because this thing is not speeding up or slowing down. We're just going to keep it simple to focus on the basics of the directional change itself. All right, and finally, we just got through a ton of stuff with Newton's laws. I spent a couple chapters on it. And especially Newton's second law, F equals ma, right? The equation. That basically tells us, both conceptually and mathematically, that acceleration doesn't magically happen, right? Things don't magically just start to speed up and slow down, right? Things don't magically change direction like this thing is. Newton's second law basically tells us if there's any kind of acceleration, what has to cause acceleration? What has to be applied? Yeah, like a force, all right? And the overall force, or if there's multiple ones, net force, as we described it in the past, always has to be in the same direction of the acceleration. Now, this particular simulation doesn't have a button to show the force vector. But if it did, it would also point inward. If there is a centripetal acceleration, and there's got to be, if we're going in a circle, then there's got to be a centripetal force that provides it, which I actually kind of already talked about a little bit without using that word, centripetal force. Remember, centripetal means towards the center. So the term centripetal force also is kind of like a general category. There's specific forces that are centripetal. One of them, we've seen a couple now, and we'll keep adding to it a little bit. In my example to start the class with the rubber stopper, the tension was the centripetal force. In this one, we said it was the friction, if this was a ladybug walking, right? So we often have to identify the specific force that's causing the circular motion. But just don't think like when we say tension can cause circular motion, we obviously know that tension doesn't always cause circular motion, right? But it can. If something can cause circular motion, it could be a centripetal force, if that's what it's doing on the object. And I know I'm saying a lot of stuff like quickly here, but throughout the week we'll keep hitting on all this stuff. I'm just trying to go over like the big overview of all the most important stuff right now. All right, so let me find my stopper that I threw. And the final concept now, and question really to ask is, I'm telling you that while something's traveling in a circle like this, that both the acceleration and the force causing it, in this case tension, is towards the center. Now, I'm not lying to you, but if the acceleration is towards the center and the force is towards the center, why, while I swing this, isn't this object actually approaching the center? Doesn't it stay on the outside of the circle? Everybody agree? So my question is, what I'm telling you is right, and it is. If the acceleration and force is inward, why, while I swing it, isn't it going inward? Any guesses? Yeah. Very good. Inertia. Don't forget, inertia is not a what? The first time we ran into that word when we define terms in chapter 4. I stressed this, but it's been a while, so you might forget. Inertia is not a what? Remember, it's not a force. All right? Inertia was a property of mass. The more massive something is, the more inertia it has. And if you put that mass in motion, the faster that mass goes, also the more inertia, or something we didn't get to yet, momentum it has. Momentum is just inertia in motion, basically. We'll learn in a little while, in a couple chapters. But anyways, this was something that was kind of debated at one point in early mechanical physics. You know, a lot of scientists were like, well, hey, if it's staying out here, there's got to be a force keeping it out there. But it's not. It's just the effects of its inertia. Its inertia interacts with the force that's trying to pull it in, and that's what causes, in this example, tension in the string. And the faster I swing this, what do you think happens to the tension in the string? Gosh, it gets more, it rises up. If you're the person swinging this thing, you could feel it. Okay? So that's because the faster it goes, the more inertial effects it has, and the more it wants to fly off. Theoretically, even though this rubber stopper doesn't weigh a lot, if I could hook this up to some kind of machine that could spin it faster than my hand can, if I got it spinning fast enough, it could probably put enough tension on this to break this string. If I get it going fast enough, because the faster it goes, the more it wants to fly off. And let me give you an example of where some of us might be familiar with this. How many of you, probably just about all of you, if you've lived around here your whole life, have gone to Idlewild before? All right, and there's many variations of this ride, but at Idlewild, I think actually may have taken it out in the last couple of years, but the Roundup, you guys know what I'm talking about? This works on that idea, all right? When you start that ride, and this will lead us in later to vertical circles, but I'm not going to go that far with it right now. When you're on that ride, does it lift you? I know it doesn't go completely vertical, but pretty close, right? Does it lift you right away? No, because what would happen if it lifted you immediately to right there? Girls? You'd all fall out, right? What it does is a ride that takes advantage of this type of physics we're talking about right here. It gets you up to a fairly high speed in a horizontal circle first, right? Remember what I said, the faster you go, the more you want to fly off, right? But that's inertia. Your want to fly off is inertia. It's not an outside force, right? It's just a property of your mass in motion. And the more you want to fly off, the more whatever force is holding you on has to be applied. Now, there's no string attached to you on that ride, right? So what is directly making you, if you're on a ride like that, go in a circle? Once you're going really fast, where do you feel like the most pressure from on that ride? Did anybody ever ride that or something like it and try to lean forward? Yeah. Right. Your inertia and want to fly off makes you really, and this is where we got to be careful how we describe it. It sure as heck feels like it's pushing you against the wall, right? But actually, it's kind of the opposite. The wall's pushing back on you. You want to fly off really bad, and the wall's not letting you. So there's another type of centripetal force, the one we're already familiar with. So we just said friction could be a centripetal force, right? Walking, driving in a circle. A string can if we're swinging something. But when a surface pushes back on somebody or something, we call that what kind of force? We always did in the past. When a surface pushes back on something. Yeah. Normal force. So in that case of a ride like that, it's the normal force providing a centripetal force on you. Because, of course, not like it could happen or would happen, but if all of a sudden when you're on that ride, if you could like flip a switch and the back of that ride would just disappear, would you continue to go in a circle? No, you'd fly off tangent to the path of the circle you're on. But anyway, back to the speed thing. It speeds you up to give you a high amount of inertia in motion. And once you want to fly off so much, you want to stay in that circular path, and the normal force is making you. And you could lift up darn near vertical and never feel a thing, right? But my thing about that ride is I just thought was funny is that little chain they put in front of you. That is completely irrelevant. If something went bad, that chain's not saving you. That's just to make you feel good like you did something. All right. But we'll look more at a rod like that next week when we get into vertical circles. That'll lead us into that one. All right, so like everything we study, there's math behind this stuff too. But before we go that far, I'm just going to show you in the notes, and these will be posted. Over here. Just recapping all the most important stuff we just said, basically. All right, so again, this topic is called uniform circular motion, and uniform basically means constant. Constant speed, not speeding up or slowing down while studying circles right now. So as we said, when we're in UCM, an object's velocity is always changing because direction's changing. That's the reason why we can't say you're going at a constant velocity. Constant speed would be accurate. Next most important thing, the velocity vectors point tangent to the path. So I just drew a rough diagram here and just put 3 different positions on some object going in some kind of circle. And if I ask you to draw velocity vectors, or you're thinking about it for answering a question, they would all point tangent, straight line in the direction. That's why when we release something, it goes in the straight line. Acceleration is present because of change in direction. Also, we said that. And we call this, that's the spelling of it, centripetal acceleration. Okay? There's another word out there that gets applied to circular motion. So we got a little bit of time, I'll discuss it right now. A term I don't have in the notes because I don't want it there, because it's really non-existent. I just told you that centripetal forces cause centripetal accelerations, right? Centripetal forces like tension, normal force, friction. There was a false term out there that was a legit term at one time, but still gets used and often used inappropriately. It was called the centrifugal force. Did anybody ever hear that before? Not centripetal, centrifugal. Remember what we just answered? Why something stays on the outer path is inertia. And one more time, inertia is not a what? Force. All right? But when this stuff early on was still trying to be figured out, some scientists called these effects of inertia the centrifugal force. But you may still hear that it's been scrapped because inertia is not a force. And that's what's making you stay on the outer path. So this term still sticks around though. And sometimes even in physics books it'll still come up, but if you read closely, it'll say that it's a pseudo force, a false force. It's not really a force. All right, but it was once defined as that. But other terms came from that term too. From the term centrifugal came the term centrifuge. How many of you ever heard of a centrifuge before? Anybody know what a centrifuge is? All right, it's really anything going in a circle that separates something, or anything just spinning in a circle in the first place. All right, sometimes centrifuges are used to separate mixtures of fluids that have different densities. One example in particular is separating blood from the plasma fluid in the blood, red blood cells from that. They're a mixture. They're not chemically combined in any way. And when medical people, scientists, whatever, for studies or whatever, want to separate blood from plasma, they spin it in a centrifuge. And because the plasma is more dense than the blood, it has more inertia, even if they're spinning at the same rate. So it goes out. It wants to fly off more. And essentially, you could create a system that makes those two separate completely and get one from the other. So that's one reason. But just centrifuges are a way to train that mimics gravitational effects. When we first learned about little g, did I ever show you the I don't know if we did that then. If not, we'll do it this week. Did I ever show you back when we learned about 9.8? Pilots and astronauts training in the videos spinning around. You guys recall that at all? Yeah? Okay. But that's applicable here too. Okay? They're in a centrifuge, and that inertial effect and the accelerations provided by moving in a circle feel like gravity. All right? Like simulated gravity, just like on that ride we talked about, right? Like if you tried to lean over on the rod like that, go in a circle, it feels like you get like sucked back like a big gravitational pull. It's not really gravity, but it sure feels like it. So we use those things like centrifuges like that to train in, or have people train in to get used to those kind of effects. But the main thing is centrifugal is not a real force. It's really just the effects of inertia, but there's a lot of terms that came from that. And as I said already, centripetal means towards the center. If we drew the acceleration vector, it would point to the center, like we showed on the ladybug. And again, Newton's law says that if there's acceleration inward, there's a force inward. We would call that specifically a centripetal force. So where we are right now, these are the handful of, and I think we named most of them along the way today, but these are the most common forces that make things go in a circle. I'm not saying they're the only ones, but almost any everyday circular motion you could identify and see or do, it's probably either tension, friction, normal force, gravity, or maybe a combination of a couple of them in some cases that makes something go in a circle. All right? Gravity, and it doesn't have to be a perfect circle, it could even be a partial circle. Even when we studied projectiles, we didn't mention this because we weren't this far, but a projectile curves, right? Why? Gravity makes it, right? So that's why it's on that list. A little bit further down the road, we'll study orbits. And orbits of satellites, the moon around us around the sun, that also follows circular motion. Even though it's technically an elliptical path, not a perfect circle, it still follows all these rules. And gravity makes us go around the sun, right? We all know that, right? The moon go around us. So those are the most typical forces that cause circular motion. And your book, I didn't put this term in the notes. Your book uses a term called the agent. And you're probably going to run into a question. I think it's a kind of a term your book made up, but it's not like a universal term. But somewhere in the next few days, you're going to have a question or a problem that says, what is the agent? Or identify the agent causing the centripetal acceleration. All that means is identify the specific force that's causing the circular motion. If I say find the agent, don't tell me centripetal force. Because remember what I said earlier, that's a general term, right? Centripetal force is just any force that can make you go in a circle. If we want to define it specifically, then we say tension, friction, normal, gravity, whatever. Okay? Just kind of FYI to know to watch out for that. And finally, as we pointed out very early, if we release this force, the object will fly tangent to the path. Just like we showed at the beginning, release it straight line from wherever I let it go. So those are all the big ideas behind this. Tomorrow, we'll spend a few minutes getting into the math and the equations to figure out some of these values. What time does this bell ring? I forget now. Anybody remember? It's soon. It's not enough time to get into the math and go into the examples. So I'll wait to post these notes until we're fully finished with the examples. All right, but they will be posted. So no homework or anything tonight. We'll go over the equations tomorrow and assign you the problems in class tomorrow. You'll probably be able to use, well, you guys will be home tomorrow, but that'll be mainly what you're doing tomorrow at home. I'll post a video of me going over the equations and going over 2 examples. Watch that, and then there'll be a handful of problems to do, okay? Any questions on anything we going over today? Kind of went through a lot there, but I wanted everybody to have the idea of these before we go into the math stuff. So I'll stop there today.